Welcome everybody. My name is Nicolas Byl. I'm working at Codecentric. I'm from Frankfurt, not from the Solingen headquarters, as some of you might know. Why do I want to talk to you about stateful applications? Well, as Peter always said, with Kubernetes and all the other Docker orchestrators, we have a very, very great platform where we can run our applications, where we can run our front ends, our back ends, and everything in between. And all this stuff, well, needs to persist data time after time. You can't go into a bank and say, oh, we have a great new platform, and well, but we can't save data to disk once in a while. And so saving data to disk is a little bit harder if you run on a platform which is by nature ephemeral. Yeah, a container is ephemeral in the place that when the container disappears, all the data that has been produced inside this container will also disappear, at least in the natural way. So, how do I run something that saves data to disks or to something where I want to retrieve it later on in such an environment? And that's what this talk is about. Usually, we start our projects. We build our front ends, our back ends, and build our database. And well, it's 2018. We have done our lead startup. We're growing, and time after time we come to a bottleneck and have a question like this. Oh, damn. We now have our great Kubernetes clusters, or cluster, if you are not that big, in front of our database, and we can grow and grow and grow and handle all the traffic that we need. But once we run our database, once it reaches the database, we run into a bottleneck because, oh, the database doesn't scale that well in a Docker environment. And you can multiply this problem if you're doing microservices, because there's a good pattern for this, because sometimes people integrate and still integrate their microservices over a shared database, like shown in this piece, where I have, for those in the back who can't see, these are the microservices, and this is the big Oracle database. And your CIO says, oh, you have to use the Oracle database because we spend a lot of money on it. And how do I integrate this with my code, my applications, into my Kubernetes cluster? That's why we are here. So, if we, as good citizens of the IT world, what is the first to do when we start going into a new project? Well, we gather requirements. So, what do we want to do? Well, we want to persist the state of our application somehow, in a way that is scalable. That's probably the easy part, that is highly available, and that is fault tolerant. And well, these things are pretty hard to achieve. So, can our platform support us anyhow? For the purpose of this talk, I want to take you through an example application where we will follow how the architecture and the infrastructure around it will evolve over the course of the talk and the things we have learned with Kubernetes and stateful applications. So this is our initial part. So we have an application. The application can be scaled pretty well. And we have a load balancer in front of it. And we have a database in the back where the applications sync their states. So all of this in this layer and this layer, we're getting this for free from Kubernetes. And for the database, what are the candidates? Well, everything you can store data in is essentially a good candidate for this. You have the classic RDBMS systems like MySQL, Postgres, some kind of the new, still feels like new kid on the block, Cassandra and MongoDB, but they are well, have been around forever. Or for those who are pretty brave, you can store your data in a Kafka. Well, just put up the retention time to indefinitely and put your data in there. All valid candidates for storing the data of our application, but they have one thing in common. They need to store the data to disks or somewhere else where we can retrieve it later on. So, just a short question into the audience. Who has used Kubernetes before? Okay. Who's running it in production? Oh. So, you can now switch off for the next 5 minutes because I will take a short detour and give a short overview over the basic building blocks of Kubernetes applications so that you all can follow through with the examples later on. So, the design philosophy of Kubernetes is that it's portable, that it's extensible, and it's self-healing. These are the values of the project that I have taken off the project website. Portable means it's running almost everywhere these days. You can run in public clouds, private clouds, in hybrid deployments. You can do multi-cloud deployments where you span your clusters over a few clouds and put them together into one cluster again. It's extensible. You have all indefinitely possible ways of integrating yourself into the cluster and doing something whenever some piece of software is doing it. You can have hooks when a pod crashes or anything like that. And the last thing is it's self-healing. It's doing an auto-placement of the containers. I don't say, okay, please start this container, this MySQL container, on this host. This is not possible. You have to define the state, the desired state of your applications inside a cluster in a declarative way. I want two containers of this one running, and it must be reachable by this endpoint. That's the way we describe our applications, and based on this description, it will be auto-restarted, it will be replicated, it will be scaled if we define some kind of auto-scaling mechanism. All that the cluster will do for you. But this doesn't make it easier to, introduce some kind of storage, because I can't say before I start an application where this will go, and I don't know, okay, is this on a host where I have a lot of storage or not? So, the most basic level of containers, or the most basic building block of a Kubernetes application is a pod. A pod is essentially a list of one or more containers that are always scheduled together. So when I have a pod which is consisting of 2 containers, these 2 will be moved around in my cluster always as one. Yeah, when the node around it, the node is actually the host or virtual machine or bare metal machine all the containers are running on. If the host dies, these 2 containers that make up my pod will be moved around together to another host where there's enough resources to run it. Okay. Anybody has an idea why this basic level can use 1 or more containers? Okay. Nobody? No, not really. So the answer was for everybody who didn't understand it, because we might need to have a second container like a Redis or anything. That's not the way, because a Redis would blow up my pod and make it more hard to schedule. This is usually used if you have 2 containers of maybe legacy applications. It's a pretty hard chunk nowadays. That can only communicate in a way that is not possible over the network. So if they talk to each other over Unix sockets or only can share data over some real local file system, that's where you need this. Otherwise, your pods will become very, very big and you will have problems scheduling them. So this is our basic building block, a pod. So if I want to somehow access a pod, I need to have an address where I can find the application behind it. And for this, we're using services. A service is an endpoint which can a gateway to one or more containers and pods, and this can be sort of some kind of load balancer. It is not an actual load balancer, but you can think of it as a load balancer in a DNS way. And well, a service name is only a DNS endpoint that's an alias for one of the containers or pods running behind it. As you can see here, we have one service, and he's hiding these two containers. This is done using a metadata mechanism, which is called labels, but I will go into it now. So everybody has an idea now how this all works. So how do I attach some kind of storage to my pods? Because in the end, they are the building blocks of my application running in Kubernetes. And if I want to run a stateful application in my Kubernetes cluster, I need to bring the storage here to my container. And the other requirement is that the storage can follow my container. And for this, Kubernetes has another object which we can store in the API and is used by the cluster, which is called persistent volume. So what is a persistent volume? A persistent volume is an abstraction of an underlying storage mechanism. It's the thing that you use when you're interacting with the cluster, but for you, it always looks like the same. You don't need to know, oh, is this NFS? Is this some kind of elastic, I think this is wrong, it should be EBS, elastic block storage. Or is this some iSCSI volume? I don't care. If I want to use this, all I need to know is about this data structure. And these data structures of persistent volumes and the storage mechanism that powers it is usually brought to you by the admin of the cluster. So if you want to use it, you need to put in another object, which is called a persistent volume claim. This is something that the user, as in the team operating the applications on the cluster, will bring with them. So I deploy my application. Okay, this is my pod. And well, I have this location in my file system, and I want to have 5 gigs of disk space over there. Okay, please use it from this claim. And now we have 2 objects who need to match each other. And if they two come together, the persistent volume and the persistent volume claim, I will have a storage that is injected into my pod down here. And from a user perspective, okay, I want to run my application and I need 5 gigs of storage at this location in my file system. It doesn't really matter how this storage actually looks like. I can have multiple types of storage in my cluster and don't care how the administrators of my cluster manage the storage and what they offer to me. Out of the box, Kubernetes supports a lot of storage systems. Here you can see at least some of them. The list is almost twice as long now, and it's growing. You have the block disk mechanism of the big cloud providers, Google, AWS, Azure, that you can use directly. You can, if you're running an on-premise cluster, you can use something from VMware, if you're running on a VMware cluster, and you have a lot of other storage mechanisms that are supported and that you can use directly in your cluster. So, one thing left, before we can use it, we need to think about access modes. The access mode of a persistent volume is, okay, what can I do with my storage? I have 3 modes that are supported. I have a read-write once, which means, okay, I can have a storage that I can mount into one pod and use it as a read-write file system. But I can use it only on one pod. Then I have read-only many and read-write many. This is actually, okay, I have a volume I can mount on many nodes at the same time, which is, okay, I must have some kind of networking file system underneath it. And I can mount them, well, read-only or read-write. And how do I use this? Well, at first I need to provision a disk which I can introduce in my cluster. Then I will create a persistent volume and reference the disk I just created. And afterwards, I create a persistent volume claim. That's the part where I go into the user side of the thing, and I mount my claim in my pod. And I've brought to you an example. Okay, how does this look like? In Kubernetes, usually you simply define your objects in YAML or JSON structures. This is actually a persistent volume. And as you can see, it has a name, it has a capacity, and we decided, okay, we need this read-write once access mode. And oh, it's based on an NFS server. And this is the location where I can get it. What is also pretty interesting and that you need to take into account if you're running this, the reclaim policy. The reclaim policy says what the cluster has to do with a persistent volume once it's no longer used. So do you want to use it again? Can it be recycled? Should it be scrubbed once it is taken out of an application? Or should we just leave the data alone? So this is just a tip, okay? This is a major source of problems if you're running in a cloud environment and say, okay, just leave the data everywhere. Please have some monitoring, or AWS will say ka-ching at the end of the month. So from the admin side to the user side, this is a persistent volume claim. And I say, okay, I have my claim, I have my access mode, and I say I need this much of space. That's all I need to define. And then I can mount it into my pod. And well, in my pod, this is what a pod actually looks like. I have a containers specification where I say, okay, I have these containers. I'm using a MySQL image, and okay, I want to mount the storage from this claim into this path around here. And afterwards, I don't need to care anymore about where my pod is running, because the storage will move with the pod around in my cluster. So, a few common pitfalls. This is abstraction, as some might have already noticed, is a little bit leaky, because the access modes, because when you need access modes that are read-write many or read-only many, you need to put some storage underneath which you can use actually on many pods at the same time. So you need to take the layer below a little bit into account. And a very common set of problems is that if you take local storage, or you take SAN storage, or network file systems, they all behave a little bit differently. And you can run into problems with one kind of storage that you might not have with another. In this case, try what suits your use case best. Okay, I've brought the demo with me, so we can take a look how this actually looks in a live environment. Can everybody read, or should I make it a little bigger? Okay, so this is a Kubernetes cluster I deployed yesterday to show you something. Okay, this is the demo. This is running on AWS. So what do we need to do if we want to attach some storage to our cluster? First of all, we need to create a volume that we can attach. And what I'm doing now, I'm creating EBS volume of a certain volume type. This is about the SLAs of the storage with a size of 5 gigs into the availability zone I've deployed the cluster into. And okay, I have a disk. Now I need the volume ID to use it in my persistent volume. Once again. Yeah, I know. Thanks. Okay, so I will now create a lab 1. Okay, I've created my YAML structure for my persistent volume, and now I will create it in the cluster. Okay, I've done a demo run yesterday evening, so my persistent volume already exists. Now we can delete it. Okay, let's go again. Okay, I have a persistent volume, MySQL data, which is now has been created, and now I want to run my MySQL server. And when I look into my dashboard, okay, we now have a new namespace. Oh, thanks. And my MySQL is running. And as we can see down here, I also have a persistent volume claim, which is bound to the specific persistent volume. And now all my data that my MySQL server is saving is saved to the EC2 EBS volume we just created. Great. Okay, we can now store data onto the disk. Problem solved, right? Not? Okay, let's go on. So, this has one problem, doing it this way. It doesn't scale. It doesn't really scale. Why? Because for every time I want to use another storage unit or persistent volume, I need to first create an EBS volume manually, parse the ID manually or by some kind of code out of it and put it into a persistent volume I just created. And well, maybe if you're running a bigger cluster and you have separate teams, we're back into the old kind of ticket hell. Oh, I need to open up a ticket for the cluster team that they provide me some kind of storage. Oh, damn. That's not what DevOps was about, right? So, can we automate this? Sure. Kubernetes has something to auto-provision these things. Because we have another problem. This process, when you're doing it manually, is error prone. Right? Anytime a human does something, it can go wrong, and you need to fix it afterwards, and it doesn't scale well. So, what can we do to make the cluster create the storage for us? Would be a much better way, right? Kubernetes has an object for this that is called storage class. A storage class is essentially, okay, here you have a blueprint where you want to where you can get your persistent volumes, and this is the default storage class when you build a cluster on AWS. It says essentially, okay, you can use this provisioner, Kubernetes AWS EBS, and well, use this kind of volume if you want to create one. There are also other types of volumes by AWS which are, well, faster or more redundant or anything like this. But in the end, I can have multiple ones of these. So for my basic applications, I use the default storage mechanism, which doesn't cost that much. And for special applications, I have the very, very performant, but very pricey other storage class. So how do I use this? Well, in the end, I only need to modify my persistent volume claim. I don't want to create the persistent volumes anymore, but in my persistent volume claim, I can say, okay, please use this storage class to provision a persistent volume, a storage unit for me, and take care of all the rest. And all I need is, okay, well, I need 8 gigs in this example. So the cluster takes all the provisioning away from me. What is supported if I do it this way? Well, you can use all the default plugins, the ones I showed you before, and that you can see on the project page. But you can have also the possibility to use so-called out-of-tree provisioners. This is as in out of the source tree of Kubernetes. There's now an interface for this. In the Kubernetes incubator, there's a project where you can find even more storage provisioners that are currently maintained by the community and not the core developers. But there's a good chance you will find something for your use case there. And well, if you're on your own and nobody has had the problem before worldwide, you can write your own. There's an example in this repo, and essentially it's 2 Go functions, one to provision and one to unprovision your storage, that you can implement and use the storage mechanism you like if you have anything else. So pretty easy. How does this work? Well, I have brought another lab, and come on. This time I have a persistent volume claim here, and say, okay, please use the default storage class to provision the persistent volume for me. Below here is a MySQL deployment and a pod, and well, I use the one from the MySQL persistent volume. So let's just create this. And have a look again. So, and oh, cool. I didn't need to do anything to have my persistent volume. Great. Now we can scale up to thousands of developers. Right. Any questions so far? Okay. But how do we do scaling? Well, if we revisit the architecture, we still have one problem. We can't scale the database well. Still, why? Because we have only one persistent volume claim. I can say, okay, please, instead of 1 MySQL container, please use 5. Doesn't work out because I have a persistent volume claim, but they are all using the same, so I can't simply scale my database. Bad. Maybe I can put something in there and different database containers right into different directories into the persistent volume claims. Nah, don't do this. Can we fix this? Sure. There's another. Oh, that's one. There's another object, and I promise it's the last one before you can go to lunch. And it's called a stateful set. And well, a stateful set is essentially a spec with 2 templates in it. It has one template for the pods and therefore the containers that we create, and it has another template for the volumes that we need to run the containers that we just create. So we have these 2 template mechanisms, and well, now we can create pods on the fly and we can create volumes on the fly. And to make scaling a little bit easier, because a lot of these applications are not very well if you simply throw random host names into your database or any kind of storage system cluster and take it out afterwards. The host names are now atomically increased. So the first host name will be port 0, port 1, port 2. I think you get it. So this is a stateful set. And essentially, it looks, well, like all the objects that we had before, put into one big one. I have a spec for my containers here, and I have a volume claim template for that I want to mount. And every time I create another pod of this spec, the cluster will create another volume, as in the spec below, and attach it to the newly created pod. And now, we're going into scale out territory, because now we can scale our databases. Because for every instance of the database, we have a separate storage. So our database will scale. We have the data in multiple storage units, so that if one of these units is being corrupted, we still have our data somewhere else. So that would be good architecture. And for this one, I brought you another lab example, because running a MySQL cluster on top of Kubernetes is not actually the easiest one, and essentially not the easiest one to produce an easy example. I've brought Cassandra, a Cassandra cluster, from the Google Samples repo, which we will now deploy. Okay. Okay, now I have Cassandra, and okay. Okay, my word log is starting up. Now I have my stateful set running a Cassandra cluster, and now it's bringing up 3 pods. And well, here they are. They're currently initializing, and well, we will go on with the talk and come back later. Okay, some wrap up. So you can do this. You can run stateful applications inside your Kubernetes clusters. The first thing you should ask yourself, I can do this, but should I do this? Yeah, because most of these data stores, they are available as managed in the cloud providers you probably use. So is there some value in running these services myself? Do I need to do this? If the answer is yes, okay, here you find some links to get started. There's a pretty good description of this whole persistent volume stuff in the Kubernetes Kubernetes manual, which is the first link. The second one is a tutorial where you can build your own stateful set, and well, how do I put this together? And if you want to test the demos yourself and well, try them at home on your own cluster, there's a download link. I will put up the slides afterwards, and well, if there's nothing left, thank you very much. Do you have any questions?